Oops. Peripheral nervous system, remember, includes 12 pairs of cranial nerves. Those are the things that we talked about at the very end of the lecture on the central nervous system. I covered those in the video that you watched, hopefully, over the weekend. 24 of those total, each one classified as either a sensory, which means that they carry signals into the brain, a motor, which means that they carry signals away from the brain, or a mixed nerve, meaning that they're like a two-lane highway carrying signals in both directions. Okay. Those mixed nerves that we saw with cranial nerves are the exact same structural makeup, functional classification of our spinal nerves. The 31 pairs of spinal nerves derives from the spinal cord. Definition of nerves: cord-like organ composed of both sensory and motor neurons, bound together by connective tissue that can transmit action potentials in opposite directions. So we said in that last lecture, some of our cranial nerves are kind of exceptions to that rule because they're predominantly sensory or they're predominantly motor. For all spinal nerves, they're mixed, meaning they carry signals like a two-lane highway in both directions. There are different designations for those 31 pairs of spinal nerves based on where they arise in the spinal cord. There are 8 pairs of cervical, 12 thoracic, 5 lumbar, 5 sacral, 1 coccygeal. In some regions, these axons from different levels of the spinal cord can come together to form what are called plexuses, which are kind of a tangled mess. Looks like a kind of spider web arrangement of nerves that then eventually break free and give rise to the nerves that can be quite large because they contain axons from multiple spinal cord levels. Actually, let me show you what a plexus looks like. I don't really get into those here in this class, but I do in my anatomy class. So if you haven't taken anatomy from me, you haven't seen these pictures. This is what the spinal cord and these spinal nerves look like. I'll zoom in. So here's your spinal cord. You can see T1, T8, 12, all the way, those are the spinal nerves that are coming off both sides. You can see where sometimes, like in the neck, they come off and then they kind of merge together, forming like the cervical plexus down here towards your shoulders, the brachial plexus, and then listed underneath of those plexuses, you can see muscocutaneous nerve, axillary nerve. Those are the nerves that eventually branch free. And then, like in the case of our brachial plexus, are the nerves that run down our arm and that kind of stuff. So it's pretty complicated, but just kind of want to talk about that real briefly. Now, going back to the spinal cord and spinal nerves, we've seen this same picture before. Talked about this on Friday when we discussed the gray matter of our spinal cord. We learned that there were what we call horns, either dorsal or posterior horns, and ventral or anterior horns. And we talked about the fact that our spinal nerves, before they connect to our spinal cord, branch to go to the back of the spinal cord and to the front of the spinal cord. We call these roots. Okay, so these are going to contain axons inside. For our posterior or dorsal root, as it's labeled here, we find inside a whole bunch of sensory neurons. Okay, predominantly or primarily, as it says, sensory neurons, where they are carrying signals in for sensations, whether it's itch or tickle or hot or cold, whatever. Okay, they carry the signal in. Remember, most sensory neurons are unipolar in structure, right? We learned that last week. Unipolar means that the cell body is off to the side, which we see one of them, but remember, there's going to be thousands of them grouped together with all their cell bodies kind of in the same area off to the side. We see kind of a fattened portion of that dorsal or posterior root, which is actually called a posterior or dorsal root ganglion, just a fancy way to describe the groupings of those sensory neuron cell bodies. Okay. Once they carry the signal into the spinal cord, they do so into that posterior or dorsal root, gray horn, where they then synapse with a interneuron, or as we also call them, association neurons. Okay. So that's the posterior or dorsal root. There's also the anterior or ventral root, which is predominantly composed of motor neurons, as you can see here. Motor neurons carrying the signal out of the spinal cord. If it's a somatic set of motor neurons, those are going to go to the skeletal muscles. If they are autonomic, like we show here, coming from the lateral horn, autonomic, remember, is going to go to cardiac muscle, smooth muscle, and glands. And the stimulation of these motor neurons allows for motor control by upper motor neurons, which are neurons in the motor areas of our brain, as well as for reflex activity, which we'll be talking about here in a second, where a signal comes in, and then it arcs right back out, and we have a response really, really quickly. These motor neurons that stimulate our skeletal muscle are called lower motor neurons because they are lower than the upper motor neurons, which are the neurons that are carrying signals down from the brain. And then they synapse and activate those lower motor neurons. So there's a set of branches to that spinal nerve right before they connect to the spinal cord, like we just showed. But right after they come out of the spinal column, which we show one vertebrae surrounding the spinal cord here, they branch again. So a short distance after passing through the intervertebral foramen, which is the opening that allows the spinal nerve to exit the spinal column, the spinal nerve then divides again. We call these branches rami, and there's kind of two major ones, a posterior or dorsal ramus and an anterior or ventral ramus. If you look at the picture, we see the size differential between the two. The anterior is much larger than the posterior. The posterior ramus supplies the somatic motor and sensory fibers to several smaller nerves that in turn innervate the backside of our body. Okay, not the entire body, but our head, neck, and trunk. So, you know, the upper half of our body, just the back of that upper half of our body. Okay, which leaves the entire front side of our body plus our lower limbs, right? Which is way more than half of our body, because we're also including the back side of the legs and the front side of the legs, which these have no connection to whatsoever. And that explains why, or should explain why, the anterior ramus is a lot bigger. Okay? It serves muscles and structure of the upper and lower limbs and skin of the lateral and anterior surfaces of our trunk. And those plexuses that I was talking about, those branches and kind of webbings, are formed when the rami from multiple spinal nerves come together. Now, a lot of this is more anatomy-based stuff, but I kind of wanted to give you a background on the structural makeup of these spinal nerves to help you understand how they function. Speaking of function, let's talk about one of the most important things that our spinal cord does, which is to serve as an integrating center for some reflexes. We talked about the function of the spinal cord white matter and carrying signals up and down, acting like an elevator. Today we're going to talk about reflexes and how the spinal cord is involved with that. First thing I want to do is just define what a reflex is. It's a quick, involuntary, stereotyped reaction of glands or muscles to a particular stimulus. Quick, it's almost instantaneous. Involuntary means that we can't control it. It's done for us. What do I mean when I say it's stereotyped? Okay, so like when you go to the doctor, have you sit on the table and they tap on your patellar tendon, right? The doctor knows what's going to happen, right? You guys know what the Three Stooges are? The not really funny show that was on a long time ago, but you know, there's always those times where, like, when you see it in cartoons as well, tap on the patellar tendon and then the doctor gets punched in the face, and because the reflex happens differently than what he was expecting. That's not something that happens in real life. Yeah, those are movie things, cartoons. Okay, the doctor knows when I tap on that patellar tendon, the leg should kick out, right? If it doesn't happen, we know something's wrong. That's why we test for reflexes, or why doctors test for reflexes. Okay, stereotype means that we know exactly what's going to happen, okay, occurring essentially in the same way every time, so the response is very predictable. Okay, There are two types, there's a couple ways to classify reflexes. The first two here that we'll talk about are spinal and cranial reflexes are classified based on where the integration takes place, where the deciding takes place, and then ultimately where the signal originates for the response, okay? So integration taking place in the spinal cord gray matter is called a spinal reflex, whereas a cranial reflex occurs where the integration is taking place in the brainstem rather than the spinal cord, okay? Cranial reflexes are a lot more complicated than your spinal reflexes, okay? We'll talk about cranial reflexes really later on in the semester. They have to do with things like, you know, maintaining blood pressure and heart rate and that kind of stuff. Okay, tapping that patellar tendon that I've been talking about, touching something hot, those responses that occur as a result of the stimulus there, hot or, you know, stretching of the tendon or whatever, those are both examples of spinal reflexes. Okay. Regardless if it's a spinal or a cranial reflex, they all share the same characteristics. They require stimulation. They're not just spontaneous actions, but responses to sensory inputs. They're quick, generally involving few, if any, interneurons and minimum synaptic delay. They're involuntary, occurring without our intent, often without our awareness, often difficult to suppress. And as I said, they're stereotyped. We know exactly what's going to happen each time they happen. We can also classify reflexes as autonomic or somatic. Based on the division of our peripheral nervous system that's involved, either the autonomic or the somatic nervous system. Now, remember, autonomic is associated with cardiac muscle, smooth muscle, and glands, right? Okay. So autonomic or visceral reflexes are going to consist of contractions of smooth muscle or cardiac muscle or the secretion by a gland. We'll discuss these towards the end of the lecture. Somatic reflexes are going to involve contractions of skeletal muscle and employ a reflex arc. Now, a reflex arc involves an action potential arching into the spinal cord and the sensory neuron, and then out of the spinal cord and a motor neuron. Here's what an illustration of a reflex arc looks like. Okay, it looks like we've stepped on or a tack has gone into the skin. Obviously, that's going to elicit a sensation of pain, right? So we've got pain-sensitive receptors in our skin. Those are the first component of our reflex arc, okay? They create a generator or receptor potential. We don't really care about what that specifically means at this time. But if we hit threshold, that means we create an action potential that propagates into our posterior horn, dorsal horn, whatever you want to call it, of our spinal cord. Okay, the sensory neuron itself is the second component. The receptor will be the dendrites of these neurons. Okay. We then synapse in our spinal cord with an interneuron, which happens to be the integrating center in this case. This is a point of synaptic contact between neurons in the gray matter of the spinal cord, or if it was a cranial reflex, this would be taking place in the brain stem instead of the spinal cord. Okay. These synaptic events determine whether the efferent, which means output neurons, issue a signal to the muscle by way of a motor neuron, which is the fourth component, carrying the signal out. So this is a somatic because this is skeletal muscle being our effector. Okay. So somatic reflexes, the effector will be skeletal muscle. If this was autonomic, it will be smooth muscle, cardiac muscle, or glands. Okay. And these are what, once again, produce the response, which really relates back to that very first lecture when we talked about feedback, where we had sensors or receptors, integrating centers, and effectors, right? All right, let's talk about some of our somatic spinal reflexes. All right, so somatic, once again, tells us we're involving skeletal muscle. Spinal tells us that we are involving the spinal cord as our integrating center. The first reflex is the one I've been talking about this morning when I was discussing tapping the patellar tendon, which is an example of a stretch reflex. We call it a stretch reflex because the initial stimulus is stretching of a muscle. By tapping on the patellar tendon, which is what's shown here in this picture, our quad muscles stretch. Is it a very drastic stretch? No, but it's enough to create this response. And we'll get to the response here in a second. Okay, first thing we need to have as part of our reflex arc are the receptors. In the case of stretch reflex, we have stretch sensitive receptors called muscle spindles. Okay, muscle spindles are dendrites of sensory neurons that wrap around muscle fibers, muscle cells. We show here in our picture in blue. They monitor the stretch of the muscle, okay, which in this case happens in the quads, creating an action potential if we hit threshold, which then results in a signal coming into the back of our spinal cord. Okay. And we see several things taking place in the spinal cord. Okay. One, where we show a signal traveling up to the brain to allow us to consciously feel and have perception over that tapping. We feel when the doctor hits our knee, right? Okay. But more important for the reflex is what's taking place here in this portion of our figure. We see positive signals and we see negative symbols, I should say. We create an excitatory response with a somatic motor neuron that carries a signal back to that same muscle. And what that means is we're going to excite this muscle, or quads, and when a muscle gets excited, it does what? Contracts. Okay. At the same time, we're also synapsing right here with an inhibitory interneuron that then inhibits somatic motor neurons that feed our antagonistic muscles, our hamstrings. Because your hamstrings are what allow you to flex your knee and like kick your butt, whereas your quads allow you to straighten your leg. If those muscles are contracting at the same time, what happens to your knee? Nothing. They cancel each other out. So we need our hamstrings to be relaxed while our quads are contracted. So we send an excitatory signal to the quads and an inhibitory signal to our hamstrings. And so our quads contract, our hamstrings relax, and what happens to our leg? We kick it out. We extend the knee. Okay. This type of reflex occurs via what we call a monosynaptic reflex arc. Mono means one. Okay. Only one synapse is crossed within the central nervous system. This also can take place at other joints by tapping on tendons at places like the elbow, the wrist, and the ankle. We just show the knee. That's probably the most commonly demonstrated time it's used. Essentially, the direct opposite of that reflex is called a tendon reflex. A tendon reflex operates as a feedback mechanism to control muscle tension by causing muscle relaxation before muscle force becomes so great that tendons might be torn. So with a stretch reflex, we cause muscle contraction. Tendon reflexes cause muscle relaxation. Okay. The receptors in this case are called Golgi tendon organs. GTOs is an abbreviation for that, or sometimes you assume called tendon organs. They are found within the tendon of a muscle, monitoring tension. Okay. So they're in tendons to detect changes in muscle tension caused by passive stretch or muscle contraction. Okay, so what's the initial stimulus? Well, tension within the muscle, which causes tension to occur in the tendon. Okay. So this reflex initiates tension is applied to a tendon, causing the Golgi tendon organs to be stimulated. In other words, depolarized to threshold. So what's happening is the muscle, in this case the quads again, contracting so forcefully that tension in this tendon is going way up. And that activates those receptors, which then results in an action potential being propagated into our spinal cord. Some of that signal is going to go up to our brain for perception. Okay. More importantly, for the reflexes, what's taking place within the spinal cord, it's the exact opposite of what we saw last time. This time, the excitatory signal is going to go to the hamstring muscles, while the inhibitory signal is going to go to those same muscles, the quads. Meaning the quads stop contracting as much or as forcefully. The hamstrings contract, pulling the leg back, and thus what happens to tension on the tendon? It's alleviated. Okay. So upon arrival to the spinal cord, sensory neuron activates inhibitory, I should say inhibitory, not inhibitor, inhibitory interneuron that synapses with a motor neuron. This inhibitory response inhibits the motor neurons, resulting in fewer nerve impulses, causing muscle relaxation, relieving excess tension. Excitatory interneurons of the spinal cord also initiate an excitatory response to the antagonistic muscles that would be your hamstrings, resulting in contraction of those muscles, which ultimately relieves tension on the tendons. So this helps prevent muscle and tendon damage. Now, you might be thinking about how does weightlifting occur? Because this is what's going to happen. Like when you're pushing, a barbell up, when you're doing a bench press or whatever, you're actually going to have to suppress this reflex, because anytime you would lift weights, you would activate this reflex. So we can actually kind of go against it. It's kind of cool. Now our next two reflexes go together. That's why I have them listed here on the same page. And they're a lot more complicated than those two that we just talked about. But they're also really cool. Okay, let's talk about the flexor withdrawal and the cross the extensor reflex. These are reflexes that I've actually been talking about since I started talking about, putting your hand on something hot, like a hot stove. And you just didn't know it at the time. Flexor withdrawal reflex, the reflex arc that allows us to withdraw a body limb in response to a painful stimulus, like touching something hot, removing the hand from it, stepping on a tack, which is what's shown here in this illustration. Okay, we call it a flexor withdrawal reflex because we flex the joint, enabling us to withdraw the limb. In this case, the knee is what's flexed, pulling the foot away from the painful attack. Okay, this type of reflex arc is similar to that of a stretch reflex because but it involves motor neuron impulses coming from multiple segments of the spinal cord. So we call it an intersegmental reflex arc, and that's why we have three different portions of the spinal cord shown in this illustration. Okay, so begins with the tack penetrating the skin, causing the pain-sensitive receptors in our toes to become stimulated, ultimately exciting a sensory neuron, hits it to threshold, signal comes into the spinal cord. Okay. Now, what takes place is not only do we activate one segment of the spinal cord, but we also carry a signal up and down the spinal cord using the white matter. Remember, the white matter is like an elevator carrying signals up and down. Okay. What happens is we send signals out from all three of those segments, and that's shown here in this illustration. Might be even more. that go to the hamstring muscles. So we activate the entire hamstring, essentially, hamstrings, because there's multiple of them. We're exciting those muscles. Those muscles then contract, and we withdraw the leg. Okay. Now, what's taking place here with the right leg is a withdrawal, whereas what we'd see with the left leg is an extension. We flex the right leg, extend the left leg in response to that painful stimulus, which is shown here on this illustration. Okay. Actually, this illustration shows both the flexor withdrawal here on the left side of the page, but also on the right side of the page, it's showing you the crust extensor reflex. So it all begins once again with stepping on the tack, causing pain to be felt, which is conscious perception, which I'm not yet ready for. But we stimulate those receptors in the toes, action potential travels into the spinal cord. And we said signals go up and down via the white matter, which ultimately causes signals to go out to the right hamstrings, causing us to withdraw the leg, right? Okay. Now, if you step on something like a tack and you withdraw your right leg from it, what do you need to do with your left leg? Shift your body weight to it, right? Otherwise, what's going to happen? You're going to crumple over and fall on the ground, right? So we also send a signal across the spinal cord using that crossbar over H. Signal goes across. We also have an intersegmental reflex arc here where signals go up and down via the white matter. Ultimately, we see excitatory signals coming out from those multiple spinal cord segments to the left leg, hamstring, or excuse me, the quads. Those contract, the left leg straightens out, and we shift our body weight so that we don't collapse on the ground. Make sense? Pretty amazing. So next time you step on something and it hurts, think about how amazing that really is as a response to move your foot off of it, shift your body weight to the other. Think about all those different steps involved with action potentials that we talked about. The voltage-gated sodium channels and voltage-gated potassium channels. Depolarization, repolarization, propagation. Look how many different neurons are shown in this illustration. Okay. Any point between the little dot, which would be a cell body, and the little fork, which would be the synaptic terminals, is a synapse. So we see all those steps involved with that as well. You know, voltage-gated calcium channels and the release of neurotransmitters and all of that wonderful stuff. Think how amazing the nervous system is, but also how damn complicated it is too. All right, we're going to move on from reflexes to some more complicated stuff, because it's all complicated. We'll start with just kind of a quick review from something we learned about last week. The two major divisions of our peripheral nervous system. Which are the somatic, which we learned is the nervous system that is associated with controlling our skeletal muscle. Whereas the autonomic, we said automatic, controlling glands, cardiac muscle, and smooth muscle. Why did I say automatic for autonomic? Because what type of control does the autonomic nervous system have? Involuntary, whereas somatic is voluntary in nature. Okay. The autonomic nervous system is composed of sympathetic, parasympathetic motor neurons, which we learned sympathetic produces what response? Like when we're being chased by a bear, we call that the fight or flight versus the, which you guys are all exhibiting right now, rest and digest, which is what your parasympathetic does. Okay. We have what we call dual innervation between these two divisions of the autonomic nervous system, meaning they have contrasting effects on the same organ. Let's just think about your heart and the speed at which it beats. When you have the rest and digest response, your heart rate is pretty low, right? What we call resting heart rate, 70 beats a minute or so. What happens though when you activate the fight or flight response to your heart rate? It goes up, right? It increases tremendously. You know, it can double within a matter of, a couple seconds and get even higher than that, somewhere around 200 beats a minute for you younger people, where it can top out at. And it's a very large, drastic increase, okay? The autonomic nervous system has what we call dual innervation, meaning that there are signals coming from the sympathetic and the parasympathetic to the same organ. And we'll talk about how the heart, for example, knows to speed up when the sympathetic activates it versus when it knows to slow down when the parasympathetic activates it. Now, just like with reflexes that we just talked about, whether it was the stretch reflex, tendon reflex, whatever, we can't have a response like a change in heart rate occurring without an input, right? Stimulus, okay? The main input to our autonomic nervous system comes from autonomic sensory neurons, primarily associated with what we call interoceptors. Intero, think interior. These are receptors in our interior, located within places like our blood vessels, monitoring stretch and blood chemistry, oxygen levels and pH levels and that kind of stuff. Within our visceral organs, the word viscera always refers to like your internal organs of the chest and the abdomen. So like the stomach is a visceral organ, heart, lungs, intestines, those are all visceral organs, as well as muscles. And we even have sensors within our brain and other parts of our nervous system monitoring conditions in their internal environment as well. We'll get into sensations in our next lecture next week because I didn't want to fit all of the nervous system in one unit. We'll have one more lecture on that at that point. Okay, reading through. Autonomic motor neurons regulate visceral activities by either increasing, we could say exciting as well, or decreasing, which we could say inhibiting, ongoing activities in their effector tissues. And whenever it's the autonomic, remember the three major effectors are the smooth muscle, cardiac muscle, and glands. Okay. As opposed to somatic motor neurons, which are usually myelinated and travel from the central nervous system all the way to skeletal muscle fibers, autonomic motor pathways consist of two motor neurons in series. And if I actually go back to the very first page, we have two illustrations, okay, both of which are carrying signals away from the spinal cord, so it's a motor division. Okay, the bottom illustration is showing you a signal coming from our spinal cord to a skeletal muscle, which tells you that this illustration is showing you the somatic nervous system. Notice the number of neurons it takes to get from the spinal cord to the muscle. It's one really long neuron. Okay, it's not going to be one, it will be thousands, but the illustration is simplified because it would be way too hard to draw on a whole bunch of neurons. The key is when you contract your skeletal muscle, that signal that's causing that muscle to contract, whether it's a muscle in your toe or a muscle, sorry, it's going nuts on me. That when I stand too close. That original signal comes from, actually it would be up the brain, but that last remaining signal for the nervous system comes from the spinal cord all the way out, which means it's a long neuron in some cases. Whereas the picture above that, we see, maybe that's the salivary gland, whatever, looks like the bladder, so that would be smooth muscle, and then obviously the heart is shown, which is the cardiac muscle. So that's showing you the autonomic nervous system. We don't see one long neuron, instead we see two. Those two neurons are called preganglionic and postganglionic neurons. The prefix pre means what? Before, and post means after. The point of, and I always use air quotes, contact between these two neurons, so where they synapse, in other words, is called autonomic ganglion. So the first neuron is before the ganglion. The second neuron is after the ganglion. The point of contact, as it states there, really should be shown in quotes, because remember, neurons don't actually touch each other because there's that tiny little gap called the synaptic cleft where the neurotransmitters have to cross after being released by the first neuron, the preganglionic neuron. So we can say neuron number one, neuron number two, or pre and post. Okay. A baton, yeah, where they hand off what we call neurotransmitters. Okay. The first neuron is located, or cell body, I should say, is located within the central nervous system. It carries the signal out. In this case, we're just showing spinal cord, but it wouldn't necessarily have to be the spinal cord because it could also be coming from the brain stem. Out of the central nervous system, we synapse. We then activate the second, what we call the postganglionic neuron, which is the neuron that releases the neurotransmitters that activate, or could say inhibit, the effectors. Okay. Now looking at the picture, we show here in the top picture the parasympathetic nervous system versus the bottom, the sympathetic, which are the two divisions of our motor division of the autonomic nervous system. All right, let's talk sympathetic here real quick. First, once again, is our fight or flight division because it adapts the body for physical activity, doing things like increasing heart rate, blood pressure, pulmonary airflow. So that's our breathing rate and the ability to get more air into our lungs and out of the lungs, blood glucose levels, and blood flow to cardiac and skeletal muscle. Remember the other day we talked about the different portions of the gray matter in the spinal cord. We talked about this picture. And we talked about the fact that there's only a couple places, or only a specific region of our spinal cord where we have these lateral horns. Only between T1 and L2 vertebrae. So like the chest portion of our body. Okay. Well, those, as you can see, are going to correspond with the sympathetic nervous system, which is where the entire sympathetic output comes from. Those lateral gray horns that was shown in that figure. Okay. So the sympathetic nerve fibers exit the spinal cord at spinal nerves T1 to L2 and lead to nearby what we call sympathetic chain or trunk of ganglia, which are a double chain on either side of the spinal cord. Okay. Here's what this looks like. For output on the right side, we showed the sympathetic nervous system. This picture is really not complete. Hey, don't worry about anything on the left side yet. I say it's not complete because there's a second one of these chains on the other side. Okay, or trunks, whatever you want to call it, sympathetic chain, trunk, same thing. These are collections of nervous tissue that would be right next to the spinal column. Okay, it runs up through our chest and neck, down into our lower back. Okay. The first neuron of our sympathetic nervous system always originates between this segment of our spinal cord, T1 down to L2. All of our output for the sympathetic nervous system comes from this division, or this segment. The first neuron, that preganglionic neuron, always leaves the spinal cord and travels to that chain. Most of the time, and if you look hard enough, you can see a dot in here. That would be the cell body of the postganglionic neuron. Most of the time, the synapse between those two neurons takes place in the chain. Which why, if I go back to this picture, we see the first neuron of the sympathetic nervous system is really short, because it's only going from the spinal cord to that chain that's on right next to the spinal column. And then the second neuron is a lot longer because it has to go the rest of the way. So we can describe the two neurons as being on equal size. The first is short. The second, the postganglionic neuron, is long. And since we utilize this segment of the spinal cord exclusively for the sympathetic nervous system, another name for our sympathetic division is the thoracolumbar division. Whereas now you can look at this other portion of our figure. We show that the thoracic and the lumbar regions of our spinal cord have absolutely nothing to do with our parasympathetic nervous system, which is what's shown here on the left. In fact, there's really not much that the spinal cord does for our parasympathetic division. Just the very tail end of it in the sacrum. A lot of our output for the parasympathetic nervous system comes thanks to those cranial nerves 3, 7, 11, and, or sorry, that's not, I'm trying to remember the numbers. 6, that's 6, so that would be 3, 7, 9, and 10, I believe. Doesn't matter the numbers, really. Okay. So we use 4 cranial nerves for our rest and digest division and the sacral region of our spinal cord, which is why another term to describe our parasympathetic nervous system is the craniosacral division. Cranio for the cranial nerves, sacral for the sacral region of our spinal cord. We also don't see the chains of ganglia involved with the parasympathetic. If I go back to this illustration, the first neuron for the parasympathetic nervous system is always long, and the second is really short. So it's the reverse of what we saw with the sympathetic. The sympathetic was short and then long. Here it's long and short. A lot of times the synapse occurs like right next to the organ that's being fed by that second neuron. Like here, you can see the synapse is right there. There's the lungs. Whereas here, it was all the way back here. And then the second neuron runs the rest of the way. Now, I told you guys this the other day. But you can think of the relationship between the sympathetic and the parasympathetic like a teeter-totter, where they are balanced. If one goes up, the other one goes down, or vice versa. We call this balance between the two autonomic tone. Normal rate of activity representing balance between the parasympathetic and sympathetic activity. Right now, you guys are exhibiting low sympathetic and high parasympathetic activity. You can see that because you're not sweating profusely and you're not breathing heavily. You're not showing those signs of, a stress situation. If I told you guys, okay, we're having the test tomorrow, I could see immediately that flipping, okay? The sympathetic would become more active and the parasympathetic would become less active. Here's another set of illustrations showing you the same things I've been talking about. At the top, we show the somatic. The signal originates in the spinal cord and it travels all the way to the effector, which is skeletal muscle. Here we show two pictures. I would label these, draw a bracket over here and label them as the sympathetic nervous system. Because there's two things that happen whenever the sympathetic nervous system is active. These two middle images are sympathetic. The bottom picture is parasympathetic. You might label that to keep your head straight. Whenever the sympathetic nervous system is active, we're carrying signals from the T1 to L2 spinal cord via our short pre and long post ganglionic neurons, eventually getting to our different effectors. But at the same time, we're also innervating the inner part of our adrenal gland, what we call adrenal medulla, where we store a lot of epinephrine and norepinephrine, which we mentioned previously and learned that epinephrine is a fancy way to describe what? Adrenaline. And we end up dumping a whole bunch of that epinephrine and a little bit of norepinephrine, as well as a little bit of dopamine, into your bloodstream, which can then carry those hormones, since they're being dumped in the blood, to just about any and every organ in the body, which produces really widespread effects like increased heart rate and constriction of certain blood vessels and the breakdown of glycogen into glucose, producing that traditional adrenaline rush feeling that we have all experienced during our lives. We'll talk more about that first thing on Wednesday.